So now we're going to look at some conservation of energy using potential energy of a spring. And just to be clear, the spring potential energy is 1/2 kx squared, sometimes written as 1/2 k delta x squared, where this x represents the displacement from equilibrium. So I have a massive spring, which is a force constant of k, where the gun is aimed vertically. A 15-gram projectile is shot to a height of 5 meters above the end of the expended spring. How much of the was the spring compressed initially? So here we're converting energy from here to energy up here, and the energy conversion is potential energy in the spring into gravitational potential energy. So the initial energy down here is just simply the potential energy of the spring, 1/2 k x squared. And that's just 1/2 k d squared, because d is the displacement from equilibrium. I'm saying this is the equilibrium point right here. Now the energy at the final state here is how much potential energy it gained in the process, and that's the height that it gained. And it didn't just gain the 5 meters, it actually gained this d meters too, right? Because if I'm really saying this is h is equal to 0. So it really contained m times g times 5 plus d. Now sometimes with high spring constants you can ignore this d. This d might be pretty small, but in this case I don't think we can ignore it because the spring constant is pretty large, so this d is probably going to be significant. So conservation of energy says these two energies have to be equal. So I have 1/2 kd squared is equal to mg 5 plus d. And 1/2 times k is times 12 is 6, so 6d squared. Mass is 0.015 kilograms times 9.8 meters per second squared, 5 plus d. And if I multiply it and distribute this out, I get 0.735 plus 0.147 d. Now to solve this is a quadratic in d, so I gotta do is put everything on one side, is how I solve quadratic equations, because I can't get d by itself. And so then d is using quadratic formula, plus or minus the square root of negative 0.147 squared minus 4 times, oh, this would be minus right here, 6 times negative 0.735, 4ac, over 2a, which is 2 times 6. And I get I'm going to get two answers, and I'm going to have to decide which one is correct. Sorry, I just keep making mistakes. 735. I get 0.362, or when I use the minus solution, I get negative 0.338. Now the problem with this solution is this implies stretching it, like I would stretch it out a little bit. But physically speaking, I can't. Stretching it out, while the energy might be the same between those two states, stretching it out is not going to launch this thing vertically. So this is not a real solution. So this is my answer. Okay. 64. A block of 500 grams attached to a spring of constant of 80 newtons per meter. So K equals 80. M is equal to 0.5 kilograms. The other end of the spring, the other end of the spring is attached to a support with mass. The mass rests on a rough surface with a coefficient of friction of 20. So mu is equal to 0.2. The block is pushed along the surface until the spring is compressed by 10 centimeters and is released from rest. So we're going to squeeze it and it's going to launch. How much potential energy was stored in the block spring support system when the block was just released? So if I'm going to say wherever it's at, say this is the compressed point. Say this is the equilibrium position, right? So it's 10 centimeters. We're going to say that we're going to say that h equals 0. So we're going to say that it has no potential energy, no gravitational potential energy at this point. But it does have spring potential energy. So that's 1/2 times 80. And it was displaced by a 10 centimeters, which is 0.1 meters. Or that's 0.4 joules. It's the units for energy. Okay. Determine the speed of the block when it crosses the point where the spring is neither compressed nor stretched. So then what's gonna happen is we're gonna convert all of this energy. It's gonna come up to this point. And at this point, what has happened, the energy here has to equal some gain in potential energy and some gain in kinetic energy, because it moved up a little bit, and it also didn't just all gain kinetic energy. It gained some potential and some potential. So this 0.4 joules, the equilibrium position is going to have some mgh plus 1/2 mv squared. Okay. The key part is I know the mass, and I don't know v, and I don't know h, but I have to compute h from this sort of triangle, and I'm going to draw the triangle in purple here to just illustrate what's going to happen. I know that it displaced 10 centimeters here, and I know this angle is 30 degrees. So I need to know the gain in the height. This height would be 10 sine 30 degrees, because this is the hypotenuse and the opposite side. Sine of 30 would be this side over the hypotenuse, right? From trigonometry. So that's what my height is equal to. So this is equal to mass, which is 0.5 times 9.8 times 10 sine 30 degrees equals 1 plus 1/2 times 0.5 times v squared is equal to 0.4 joules. Oh, actually, a little bit tricky because we have some friction. Let's not forget that. Plus the work done by friction will equal 0.4 joules. Okay. Now, why do I add it to this side? Well, because overall, this is going to be lower energy when there's friction being done. So I'm going to add in the work done by friction. And so we have to do a free body diagram to find the force of friction times its distance, right? That's what the work done by friction is. So the force of friction is just mu times the normal force times the distance. And the normal force in this case, if I were to draw a free body diagram, hopefully we're good at this point. This is mg. This is the normal force. The normal force just equals mg cosine theta. So what I'm going to do instead is just keep these in symbols for a little bit. So before I factor in the friction here. So m times g times, we're going to call this, this 10 centimeters I'm going to call d. Okay, that's d. d times d times sine 30 degrees, sine theta, plus 1/2 mv squared, plus the work done by friction, which is mu mg cosine theta times d, is equal to 0.4. And so I'm going to divide by m. Well, I could factor out an m. Well, basically I'm going to move all this to the other side and then divide by m. So I'm going to have 1/2 mv squared is equal to 0.4 minus mg d sine theta minus mu mg d cosine theta, divide by m, multiply by 2, get rid of that, and then so all of this divided by m, all of that times 2, and then square root of all of this. 0.4 minus 0.5 times 9.8 times 0.1 sine 30 degrees minus mu is 0.2, 0.5, 9.8 times cosine 30 degrees divided by 0.5, and then all of that times 2. Okay, so this is what I'll put in my calculator. me see. I seem to have gotten 0.5. Actually, it's not... I don't think it's 10 centimeters. Let me think. It's going to be less than 10 centimeters because of this. Because what I ended up getting when I did this expression, I got a negative number up here, which means I went too far. I think, because we said 1/2 kx squared is 0.4. So I did 0.4. Let me just make sure I did this math right. Minus 0.5 times 9.8 times 0.1 sine of 30 degrees. Minus 0.2 times 0.5 times 9.8 times cosine of 30 degrees. Yeah. So I want to know when the spring is not stretched or compressed. So physically, what's going to happen? I'm going to compress it, and it's going to do it. How much potential to determine the speed above across the point? I don't think it makes it all the way back up. Well, I guess it must. So I got a negative answer on this top part, and that's what I'm trying to sort out. Oh, I didn't do this. I didn't multiply this by 0.1 here. That's what I messed up here. That was supposed to be D. I forgot D there. Okay, good. Then divide this by 0.5 and then times 2. And then square root of that. And so I get the velocity to be 0.53 meters per second. Okay, good. Sorted that out. Determine the position of the block where it comes just the rest on the way up the incline. So now it's a little bit different. I want to know in my setup on the equation, what is the maximum distance? So I want this part to be 0. But here I don't know what D is, right? So I'm going to make this 0, and I'm going to figure out what the D is. The D is not 10 in this case. So for C, I'm going to use my same equation. I'm going to have mgd sine theta plus mu mg cosine theta times D is equal to 0.4. And now I'm going to factor out a D. And I might as well factor out an mg while I'm at it. Mg, and I get sine theta plus mu cosine theta equal to 0.4. And so the D is going to be 0.4 divided by mg times sine theta plus mu cosine theta. Because that's the furthest it goes when the velocity is 0. That's where all the energies converge. So 0.4 divided by 0.5 times 9.8 times sine of 30 degrees plus 0.2 cosine of 30 degrees. Hmm. 0.4 divided by 0.5 times 9.8 times sine 30 plus 0.2 cosine 30. I get 0.121 meters. Okay. Thanks for watching. If you enjoyed this video, I go through a lot more of these exact kinds of problems with much longer videos on my website. It's entirely free. Check out the link in the description below.